Well, now we are coming to a mode of explanation of Newton's third law of motion. Well, the statement is the same. When the law was made about 3 or 4 centuries back, the same statement is continuing now also. But we can modify the same statement to certain extent. So Newton's third law of motion states that to every action there is equal and opposite reaction, but we find that this is not followed by a ball which is descending, or when the ball is dropped from a certain height, it is striking the ground and rising up, but it does not go to the same height. So we find that during collision, there is possibly some loss in energy, being the collision is not perfectly elastic, and that's why after striking the ground, the body is not going, or the ball is not going exactly to the same height. So third law of motion is in the modified form can be spoken as that action and reaction are equal if collision is elastic. At the same time, no collision is perfectly elastic. So third law of motion, that is action reaction are equal when collisions are elastic. Now the rocket engine is indicated here. The exhaust flow pushed backward and the rocket is moving forward. So what we are finding that action and reaction are taking place. That is, gases are going backward and the rocket engine is moving forward. So up to the time the gases will be exhausted out in the backward direction, we find that the engine will move forward. This is what depicted in this animation. Now, the third law is stated, which I have already explained, that to every action there is equal and opposite reaction. Then it is written F12, that is force on one with respect to second body, and F21, force on second body with respect to first body. So F12 is equal to F21. That is, action and reaction act on the different objects, but act simultaneously. This law can be obtained from the second law, and the second law is stated as that force is directly proportional to rate of change of momentum. That is, F is proportional to dp over dt, or dp over dt can be written as mv minus mg over t. Now there are certain examples. First is the case of bullet and gun. When a bullet is fired from the gun, we find that bullet moves forward and gun moves backward. There is a slight jerk to the gun and it goes back. So on firing a bullet from gun, a jerk acts in the opposite direction. That is, the rifle will move backward. Bullet is going forward. Now, this backward motion of the rifle is sometimes known as, that is, the recoil, or this event is called the recoil of gun. Now, launching of a rocket or motion of jet airplane, that is also an example of the third law of motion, because while launching the rocket, we find that the fuel is burned, fuel comes out, and the rocket moves forward. So action is fuel coming out, and the reaction is, that is, rocket moving in the direction opposite to the ejection of fuel. Similarly, in the jet airplane, we find that gases move backward, they are ejected out from a capillary type of nozzle at the back point of the airplane, and the airplane moves forward. Similarly, there is an example of the pulling of the horse and cart. Then it is moving of a boat in the opposite direction due to jumping of man from the boat. In case of boat, what we find is that once the person is jumping, moving forward, the boat will be moving backward. So this is depicting action and reaction are equal. Now, next discussion is regarding the free body diagram. So in the free body diagram, we consider an object and external forces are acting on it. So when external forces act on a particular mass, that depiction of forces on the body is called free body diagram. So we can say like this, a diagram that shows that all external forces acting on an object, the body will be known as the free body diagram. In a specific problem, first we are required to choose a body, then we find that the number of forces acting on it, all the forces are drawn on the body. So this is shown in the figure, considering it as a point mass. So all masses are first of all assumed to be the point masses and the forces are acting on it. We draw a figure for that and that figure is representing a free body diagram. This is depicted in the example as well as in the diagram. The first figure, that is the A figure, is representing a free body diagram of a bigger mass and a smaller mass, that is capital M and small m, forces acting on it. Similarly, B figure is indicating the free body diagram of R1, mg, F and F1. Similarly, the third figure is indicating that there is a small mass, the normal reaction is R1 and the weight is mg. So it is a free body diagram because F1 is acting on mass n. So for example, if two bodies of masses small m and capital M are in contact and a force F on M is applied from left, that is figure A, as I have just now depicted, it is a free body diagram of M and M. The second figure is a free body diagram of F, M and M. And in the third one is free body diagram of F1 and small m. All diagrams showing in all external forces acting on an object is called free body diagram. Again, it is depicted in the figure. So these are the free body diagrams in the three cases, one for capital M and small m, other for capital M, and the third one is for small m. Forces are acting on all the cases. One of the very important point is that two forces in the Newton's third law never occur in the same free body diagram. This is because a free body diagram shows forces acting on a single object and the object is supposed to be a point mass. And the action-reaction pairs in Newton's third law always act on the different objects.